Picture the most solid, impenetrable thing you can imagine. The dense foundation of a mountain, perhaps. The unyielding bedrock far beneath your feet. For all of human history, the ground beneath us has been a symbol of absolute stability, of dry permanence. But that perception is now an illusion, shattered by a discovery so counterintuitive it feels like magic. What scientists have found is that the very definition of rock changes under the conditions that exist 400 miles inside our planet. Down there, in a layer geologists call the transition zone, the rules of our world are written by unimaginable pressures over 0 times what we feel at the surface, and searing heat. And under those rules, a remarkable mineral called ringwoodite undergoes a transformation. This isn't about finding underground lakes or rivers. This is something far stranger and more profound. Ringwoodite has a crystalline structure that, in this deep Earth environment, becomes desperate for hydrogen and oxygen. When it encounters even the most minute traces of water, perhaps from a sinking tectonic plate that has carried a bit of ocean floor down with it, it doesn't reject it. Instead, it performs a kind of atomic alchemy. The mineral's structure opens like a microscopic cage and swallows the water molecules whole, not as a liquid, but by breaking them apart and locking the atoms directly into its own geometric lattice. The rock doesn't get wet. It becomes something new. It becomes a hydrate, a stone that is, by its very chemical nature, part water. So, envision not a dark cavern filled with water, but an endless, pitch-black landscape of this special, deep earth rock, glowing with interior heat. And within every cubic meter of that rock, its atomic matrix is studded with the essential components of H2O. It is a desert that is also a reservoir, a solid ocean. The water is utterly invisible, completely bound, yet inescapably present. It is the most significant hidden stash of water in the solar system, and it has been sitting right below our continents this entire time, a sleeping giant in Earth's deep interior. This changes our understanding from searching for bodies of water to recognizing a state of being. The planet, in its deepest reaches, is literally saturated. It means when we speak of Earth's water cycle, we must now think in terms of millions of years and hundreds of miles of depth, a slow, colossal pulse where water is carried into the incandescent, dark on sinking stone, imprisoned in glittering crystal cages, and then later, perhaps, released by an upwelling plume of heat to begin its long journey back to the light and to us. The story we've told ourselves about water is a story of arrival from somewhere else. For generations, scientists have painted a dramatic picture of the early Earth, a hellish, molten world, bone, dry and barren, relentlessly bombarded for hundreds of millions of years. The heroes of our existence were icy wanderers, comets, and water, rich asteroids smashing into this desolate rock in a cosmic torrent, delivering, drop by precious drop, the very essence of our oceans. It was a compelling origin story, one that placed the source of life itself in the distant, frozen reaches of space. This new discovery turns that narrative inside out, quite literally. That immense, bound ocean locked within Earth's mantle isn't a later addition. The chemistry suggests it has been there for a very, very long time, likely since the planet's violent formation over 4 billion years ago, which means the water wasn't just delivered to the Earth. It was part of the Earth's essential recipe from the very start. Think of it not as a coating applied to a finished sculpture, but as an ingredient mixed into the raw clay before the sculpting even began. This reframes everything about our planet's infancy, the chaos of planetary formation, the colossal collisions that built our world, didn't create a dry ball waiting for a celestial watering. They forged a planet that was, at its heart, wet. The water was there, trapped within the swirling, accreting material of the primordial solar system, and it was buried, preserved, as the young Earth differentiated into its core, mantle, and crust. Our oceans, then, didn't fall from the sky so much as they emerged from the deep. They are the product of a great geological sweating out. The planetary scale implications are staggering. It suggests that water might be a far more common feature of rocky planet formation than we ever dared hope. If our own planet, forged in the hot, inner region of the solar system, retained this monumental reservoir, then countless other Earth-like worlds orbiting other stars could have been born with their own deep, primordial oceans. The search for life beyond Earth often focuses on the Goldilocks zone, the orbital distance where liquid water can exist on a surface. But what if the most important water isn't on the surface at all? What if it's baked into the foundation, a guaranteed inheritance from a planet's birth, waiting for the right geological conditions to rise, to seep, to manifest? It shifts our perspective from planets that receive water to planets that are water, at their very core. Our blue marble, with its shimmering surface seas, may not be an exception. It may be the rule, revealing a universe where the potential for oceans, and perhaps for life, is not a fragile gift from the stars, but an intrinsic part of a rocky world's birthright. Imagine the world below your feet not as a solid, silent mass, but as a slow, moving symphony of stone. A geology of immense, patient forces, the grind of continents, the rise of mountain ranges, the deep rumble of volcanic fire. For centuries, we have studied this symphony by its surface notes, inferring the hidden melodies. Now, with the discovery of this vast, bound ocean within the mantle, we have finally heard the bass line, and it changes the entire piece of music. That water, locked inside ringwoodite 400 miles down, is not a passive prisoner. It is a master conductor of geological energy. Its presence there, in that churning layer of hot rock, fundamentally alters the physics of our planet's interior. Pure, dry rock under that kind of heat and pressure behaves in one way. It is viscous, stubborn, resistant to flow. But introduce even a tiny percentage of water, locked into the minerals at an atomic level, and everything changes. Water acts as a potent flux, a lubricant of almost unimaginable scale. It weakens the chemical bonds between the other atoms in the rock, making the solid mantle. Less solid, it becomes more plastic, more willing to deform, to creep, to move. This is the hidden engine behind the world we see. The giant tectonic plates that carry our continents are not sailing on a static sea of rock. They are the visible, surface expression of a vast, convective engine within the mantle, hot rock rising, cooler rock sinking, in a cycle that drives everything. That deep, hidden water is what allows this engine to run smoothly. It greases the gears of the planet. Without it, this convection might be sluggish, stagnant. The plates might lock. The great geological rhythms that shape our world could seize up. This explains mysteries that have long puzzled geologists. Why do we see certain patterns of volcanism, like the fiery ring that encircles the Pacific Ocean? It is tied to the deep water, assisted recycling of oceanic plates back into the mantle. Why do some plumes of superheated rock manage to melt their way up from the very edge of the core to create volcanic island chains like Hawaii? Their journey is made possible by the way water lowers the melting point of rock, creating pathways of molten material through the solid mantle. Even the very existence of our continents, the stable landmasses we live on, may be tied to this process. The water deep below influences how and where the buoyant, granitic rock of continents is forged and remelted over billions of years. We are witnessing a profound unification of Earth's systems. The water cycle is no longer just the familiar journey from ocean to cloud to rain. It is a grand planetary loop. An ocean plate, heavy with waterlogged rock from the seafloor, dives at a trench, carrying surface water down into the realm of ringwoodite. There, the water is stripped and absorbed, altering the mantle's behavior for eons. Later, that same water, released by an upwelling plume, might fuel a massive volcanic eruption, exhaling steam into the atmosphere to begin the cycle anew. The rain that falls on you today contains molecules that have not just traveled across an ocean, but through the heart of the Earth itself. The ground beneath us is not just land. It is a participant in the most profound and ancient recycling program in existence. The story of life on Earth has always been a story written on the surface, in the oceans, along the shorelines, in the soil. But what if we've been reading only the last few chapters of a much longer, and much deeper, saga? This discovery of a planetary, scale reservoir of water, hidden in the mantle, forces us to reconsider the very stage upon which the drama of life unfolded. It suggests that the stability and longevity of our surface oceans, those vast, life-nurturing basins, are not a happy accident, but a carefully regulated feature, sustained by a deep earth wellspring. Consider the fragility of a surface, only water world. If all of Earth's water were simply perched on top, exposed to the relentless processes of space and geology, it would be a volatile, precarious system. It could be lost to space, locked away in minerals, or undergo catastrophic fluctuations. But the hidden ocean changes that equation entirely. It acts as a colossal buffer, a planetary thermostat and stabilizer for Earth's most precious resource. This deep, bound water is part of a slow, majestic exchange, a safety valve of geologic proportions. When surface water is pulled down into the mantle by subducting tectonic plates, it isn't lost, it's banked. It is stored in that immense crystalline reservoir, a savings account holding quadrillions of gallons. Conversely, when volcanic activity or mantle plumes release some of that deep water back to the surface, through steam in colossal eruptions or the formation of new crust, it represents a deposit back into the active system. This grand billion-year cycle means the oceans we see today are not the original, dwindling puddles from a cometary deluge. They are the visible, active portion of a close-loop system of staggering size and stability. The mantle is not a dead end. It is a deep, regenerative heart, constantly circulating life's most vital element. This reframes our search for life elsewhere in the cosmos. For decades, the mantra has been "follow the water" on the surfaces of other worlds. We've looked for dried riverbeds on Mars or the icy crust of Jupiter's moon Europa. But if Earth teaches us a new lesson, it is that the most important water may be the water you cannot see. A planet with a parched, barren surface could, in theory, still harbor a deep, hydrous mantle, a subterranean oasis on a planetary scale. The conditions for life, as we know it, require not just water, but persistent water, a stable, enduring environment where chemistry can experiment for eons. What provides that persistence better than an entire planet's worth of rock, primed as a water reservoir? The emergence of life on Earth may not have been a spark struck on a wet rock, but a process coaxed along by a planet that was, from its very core, committed to maintaining its wetness. It paints a new picture of our own planet's biography. We are not living on a rocky sphere that was fortunate to catch some passing ice. We are the inhabitants of a world that was born wet, that manages its water with deep time wisdom, and that has, for over 4 billion years, used its own fiery interior to protect and recycle the very essence of its living surface. Our blue planet isn't blue by chance. It is blue by deep, enduring design, a design written in water and sealed in stone far beneath our feet. Consider for a moment the way we have always measured a planet's potential. Our most powerful telescopes scan distant stars not for the glint of surface oceans. That is often an impossible hope across such distances, but for subtler clues, the wobble of a star hinting at an orbiting world, the faint dimming as a planet transits, the theoretical calculations of a habitable zone. This zone, a band not too hot and not too cold, has been astronomy's gold standard. It is where we believe liquid water could, theoretically, exist on a rocky surface. But this new understanding of our own Earth introduces a profound and humbling caveat. We have been judging the book by its cover, and we may have been wrong about the story entirely. The revelation of Earth's deep, primordial ocean suggests that a plan, its most vital resource, may have nothing to do with its distance from its sun. The water was here from the beginning, not as a surface feature, but as a foundational ingredient. It was mixed into the batch, not poured on top after baking. This means a planet that formed in what we would call the hot inner zone of a solar system, a place where surface water would instantly boil away, could still be born absolutely drenched, its water safely sequestered in a mantle of water bearing minerals. Conversely, a frosty world in the outer reaches might have its water all locked in surface ice, with a dry, inert interior. The traditional habitable zone begins to look like a rule for where life might be visible to us, not where it might actually exist. This discovery, therefore, is not just about Earth. It is a new lens for the cosmos. It forces us to ask a different kind of question about every rocky exoplanet we find. Instead of just, is it in the right spot, we must now ask, what is it made of deep down? The potential for a stable, long-lived hydrosphere, the true prerequisite for life, may depend less on orbital address and more on planetary chemistry and interior dynamics. A world with a churning, wet mantle could be volcanically active, could outgas water to form transient surface seas, could have a deep, hot biosphere in its crust, or could simply be waiting for the right geological moment to express its inner ocean. Life, in its most tenacious forms, might not need a sun-dappled ocean. It might thrive in the dark, high-pressure frontiers where that deep, bound water meets energy from a planet's hot core. Our perspective on our own solar system shifts too. We look at a bone, dry Venus, a planet often called Earth's evil twin, with new curiosity. Was it born wet? Does its hellish mantle still hold the ghosts of oceans past? And Mars, a frozen desert, prompts a deeper inquiry. Did it lose its surface water to space, or did some of it retreat inward, locked away in a deep, frozen mantle? We are learning that a planet's history is not just written in its canyons and craters, but in the hidden, mineral-bound memory of its deep rock. Ultimately, this teaches us a lesson in cosmic humility. The universe's recipe for a living world may be more robust, more common, and more hidden than we ever imagined. We are not a rare, fragile miracle perched in a perfect, narrow band of light. We may be one expression of a universal process, a process where water is a standard issue in the construction of rocky planets, and life is a patient, persistent possibility waiting in the dark. Wet heart of countless silent worlds. The search for life becomes less about finding another Earth in a telescope and more about learning to listen for the slow, deep pulse of water in the rock of distant spheres.